All right, why don't we go ahead and get started? Welcome back, everybody, to the last class of Python for Physics. It's hard to believe it's been, in some ways, 8 long weeks. In other ways, it's gone pretty fast. So I can say that it's been a pleasure having these classes with you, even though we are, at a distance. It's still been really nice to interact with you remotely. So I figured, since this is the last class, I would introduce a series of new concepts, some of which we've hinted at or touched on in the past. But these are concepts that we haven't introduced in Python for Physics before, but we thought that it would be quite a bit of fun to cover. So these are going to be, we're going to start with thinking about electromagnetic waves, introduce integration. We're going to touch on Fourier transforms, and also in doing so, introducing some basic concepts about complex numbers. Some of this might be things that you haven't seen before. That's perfectly fine. The point of this is to introduce you to new ideas. And then hopefully, if some of it is not immediately accessible to you, it can be in the future. And so you can come back and look at the videos whenever is best suited for you. So let me start with some for the last time, administrative stuff. This is our email. If you're new to this class, welcome. This is the last class of an 8-week series. But you can look back at the older videos and catch up on everything. And to have access to this, what I would encourage you to do is send us an email to pythonforphysics@odu.edu. This email is going to stay active long after we stop recording this video. So you will be able to still email us, and what you will get is an auto reply with this information. The first link is our website, which you can go check it out. We have a lot of information there, including a lot of your nice quotes. So as always, let me stop for a second and say, since this is the last time we're going to be interacting, why don't you tell us how you're doing? We like hearing from you. We like hearing your thoughts and seeing what you think of the class. So feel free to just send us a comment in that comment box right now and tell us how you're doing and how you're enjoying the class. What are some of the topics that you wish we would have covered? And we can think about this for the next installment of Python for Physics. And the second link that you will get is this link, which will take you to a Slack chat where you can talk to us, the faculty, as well as our TAs. And so you should do that. One caveat is that you have to be 16 years of age or older. The live streams are this. There's a link, but this is the last day of live streams, so this is going to be slightly useless starting from today. But the other links that you will see are the recordings. And so this will take you to the previous sessions if you missed them. This is what our website looks like, and we have a lot of information there, so please take a look at it. Okay, so I figured I would do a mini review of the ideas that we introduced in the last class. So on Tuesday, we had a special talk from Dr. Aslan on an introduction to quantum mechanics. If you didn't see that, I would highly encourage you to check it out. It was a lot of fun. And so I'm going to skip over that because we didn't introduce any new Python-related concepts there. So this is a review of the class before that. And there we introduced a model which is a simplest model for understanding how infectious diseases evolve inside of a population. The idea for this, even though it was not physics, is that it seemed timely and involved solving differential equations, which we introduced how to do that the week before, how to solve differential equations, that is. So the simplest model was called the SIR model. This is the second simplest one, which is the SIRD model. And what this does is what this model is a model that grabs the whole population in some area and it breaks it up into 4 buckets. One is the people that are susceptible. The other one is people that are infectious. And then the other 2 are people that have recovered or those that have been deceased. And so the the way the basic equations of this model describe is the evolution of people that are susceptible to those that are infected, but via the interaction with infected people. And then ultimately, the infected people can either get better, and so they would land on the recovered bucket, or they can pass away, in which case it would fall under the disease bucket. And so this model is not too hard, and we walked through the steps on how to write the equations that relate each one of these populations together. And one thing that is worth noting is that at all periods of time, the sum of all of these different buckets has to be equal to the total population. So that gets fixed. And so this is a little animation of how the evolution happens, right? So people that are here can go into infectious people, and then the infectious people can either land in the recovered category or under the disease category. And so we were able to derive in some detail the equations that describe the evolution of each one of these populations. So we wrote an equation for the susceptible people, for the infectious people, for the recovered population, and then the diseased population. These equations were discrete. So here, this delta is emphasizing that we're making a variation that is discrete rather than continuous. You can take the continuous limit and write differential equations, and we did that. But for numerical purposes, it's much more convenient to think about this discrete forms. And so we were able to then show that the solutions of these equations have to satisfy this form. And so we were able to write down 4 iterative expressions for these 4 different populations. And so the task that we left you to do was it was just 2 simple exercises. So simple under quotation marks, right? First one was to write code to solve these differential equations. And so we already wrote down the iterative form of the solutions. And so what you have to then do is write code that would do essentially a for loop. That's about it. And then just iterate the solution, these expressions in the previous slides over the amount of time that you're interested in. Okay. And so this is an example of what our code looks like. So we encourage you to do something independent of this and perhaps look back if you're stuck, as always. So this is what it looks like. And then the second exercise is we set some conditions for the parameters of some values for the parameters that describe the evolution of these populations. And then we set some initial conditions. And we asked you to then plot the infectious and the diseased population as a function of time. And this is what you should have gotten. Okay. So hopefully some of you got a chance to look at that. If you had any problems or questions or confusions, now is a great time to ask them. So feel free to send those either to the comment box or our Slack chat. Okay, so maybe I'll stop for a second and see if the TAs have any questions, comments, or anything worth reading before introducing some new concepts.
Yeah, we have a couple of nice comments from some of the students out there. Jayu Chao from Chiai, Taiwan says, I'm doing great and it is quite sad, but yet a sense of pride as this is the last class where I am proud of myself for sticking these weeks and also the hard work I did for all the fun projects. Sad that this is the last class and it was really fun and informational. Hope there will be similar installments in the future. Hope you guys are doing great and have a great weekend.
That's awesome. That's great. Thanks so much for that nice comment. Okay. Anything else, or should I go on?
There's actually another nice comment that just came in from Jamie Madera in Puerto Rico. They said, good afternoon, Raul. I just wanted to mention that they got their certification in Introduction to Python, and they wanted to thank you for motivating me in the first place to learn a new language. Thank you.
Oh, that's amazing. Well, I'm glad we're really happy to do this for you guys, and that yeah, it makes us so happy that you get that people around the world are taking advantage of these resources. So thank you so much for those nice comments. Okay, should I go ahead and get started, or anything else that we should cover? Just go ahead and get started. Sounds good. Okay, so let's start with something fun. Just kidding. Everything is going to be fun today. So I'm going to start with something fun, and I'm going to end with something fun. There you go. So let's start with thinking about electromagnetic waves. So I think a few weeks back, I introduced Maxwell's equations. My brain is a little fuzzy these days, being stuck at home. So if I didn't, let's walk you through it once again. So Maxwell's equations describe they're four equations. And they're the fundamental equations that describe the interaction between electric fields and magnetic fields and charged particles. And they can be summarized quite simply in these forms. So there's four of them. They have different names associated with people that originally found them. Maxwell was the one that cleverly tied them up all together by making a slight small but important modification to the last equation. And so the first one is known as Gauss's law, which is I should be more specific, it's Gauss's law for electric fields. And it tells you E here is the electric field, B is the magnetic field, okay? And so this equation, what it tells you, and I should maybe cover each one of the symbols. So rho is the charge density. So it's just telling you how much charge there is in some volume, okay? And J is the current density. So it's telling you how much current, which is charge that is moving. So it's in particular, current is defined as the change of charge over the change of time. So it's really the time derivative of charge. Now that you know derivatives, so there you go. That makes it much easier to describe it. But it's the current density. So it's the amount of current per volume, okay? And so the first equation is telling you that electric fields can be generated from charges. Very good, right? The second one tells you that there's no, so this is a complicated derivative acting on the magnetic field. And what this is telling you is that there's no magnetic charges, okay? Just like there's electric charges, there's no magnetic charges, okay? This second equation is telling you that you can generate electric fields from a time-varying magnetic field. So you can create, if you vary the magnetic field, then you can create a electric field. And then the last one is that it's telling you that you can create magnetic fields either from moving charges, so charges that are moving, or by time-varying electric fields. Okay, so notice there's some symmetry here that appears between between the magnetic field and the electric field in these equations. And so Faraday's law is this one, Maxwell's equation is this one. And I should make a note, which I commented on before, that the reason why Maxwell gets credit for the unification of these equations is just because of that, because he managed to show how these equations are tied together, they're unified. And so it made it that much more apparent that electric and magnetic fields are really two different components of one greater field. And so it's the first time that we had two seemingly different phenomena tied together and unified into one composite phenomena. And so this really inspired Einstein and many others since then to try to find some way to grab all the forces in nature and describe them in terms of one unified theory. Right now, we haven't been able to achieve that, but it's not something that people have totally lost hope on. So we have unifications between the electromagnetic force, the strong nuclear force, and the weak nuclear force. But then there's the pesky gravity, right? And so there's a lot of work in trying to unify these four, and perhaps even extensions of other forces that we know that have to be there, but we haven't really conclusively found. Okay, so electromagnetic waves, which is what I'm going to be talking about. How do they come about from this equation? Well, you can see that from Faraday's law, we find that time-varying magnetic fields generate electric fields. So if I vary the magnetic field is a function of time, right? That will generate an electric field. And then from Maxwell, what we find is that, or what Maxwell found is that time-varying electric fields generate magnetic fields. Okay, so if we put these two together, right? So for the first one, if I vary the magnetic field, that will lead to electric fields. But if I vary the electric fields, then that's going to lead to magnetic fields. And so if I grab these two basic concepts together, that tells me that from electric fields, I can generate magnetic fields, from which I can generate electric fields, from which I can generate magnetic fields, and so forth and so forth. And so with this basic idea is that if we have disturbances in the electric field and magnetic field that can then propagate through space, these are what are known as electromagnetic fields. Electromagnetic waves. Electromagnetic waves are different than waves that we're much more familiar, right? Like water waves, because they don't travel, they don't require a medium for them to travel, right? We need water waves travel in water, sound waves travel in air, right? So you can't have sound waves out in space, but light does travel without the need of a background, okay? So they're peculiar, but otherwise, mathematically, they don't look that different than other kinds of waves. And so let's do a simple derivation of what these electric and magnetic waves have to look like. So imagine that I'm in a region, so I have some charge over there, right? And the charges are wiggling around. And so because of that, because they're charged, they're going to create electric fields, but also because they're wiggling around, they're going to create magnetic fields, okay? So imagine that they created these time-varying electric and magnetic fields, and they're propagating, and eventually I see them, right? But in the region that I'm seeing them, there's no charges, okay? So they're created over there from far away, and then they're in this region, there's no charges. Okay, so I'm going to I want to understand what the consequence of these equations are in the region where there's no charges. So because there's no charges, the charge density is 0. Because there's no charges, the current density is also 0. So this is the region that I'm considering. In this region, Maxwell's equations simplify quite a bit. The first two of them are kind of trivial, so I don't need to think about them. But the last two, right, are important, or they play a much more important role. So I can rewrite, after some mathematical magic, I can rewrite these two equations, Faraday's law and Ampere-Maxwell's equation, in terms of two equations. So I can replace those two equations with two other equations, right? So I have two coupled equations where I couple in the electric field and magnetic field, and I can replace these with two equations where I have a simple expression for the electric field and then a simple expression for the magnetic field. And these are what those equations look like. So let's look at the first one. The first one, I'm taking the derivative of the electric field with respect to position twice, okay? So I'm taking the derivative once and then the derivative twice. Okay, you're familiar with derivatives, right? So now this just means I'm going to grab the electric field at some point and then take the electric field at a point before. So, and then I take the limit and then I divide that difference by the difference of the distance between those 2 points, and I take the limit as that distance goes to 0. And if this is not absolutely clear, we'll remind you how to do this in just a second. So that's what this means, right? The second thing is the same thing. I'm taking a derivative twice, but not over space, but rather of time. Okay? And then there's this factor of c. This c squared, is the speed of light. Is the speed at which the light is traveling. Okay? And what you see, if I look at this equation and I look at the other one, I see that the magnetic field has exactly the same equation, right? They both satisfy the same equation in this case. And what these equations are, these are known as wave equations. And this is one of the most important, I see a typo, let's correct it. Most important differential equations in physics. And is a differential equation of, just like we've seen differential equations, so the electric field satisfies this differential equation. The only difference that is different from, so it's a second order because you're taking two derivatives, right? But it's also a partial differential equation. What does that mean? That just means that I'm taking two derivatives with respect to two different variables. So what we've seen so far are ordinary differential equations where you're only taking derivatives, any number of derivatives, with respect to one variable, and the function only depends on one variable. In this case, it depends on two different variables, and so we give that a different name. Okay, so it's special. And so for a nice introduction into waves, so we got a little bit of a picture of what waves look like. I would encourage you to look at Dr. Aslan's previous talk for a nice depiction of waves. But we'll talk about them in a little more, in quite a bit more extent here. And the claim is that the solution to these equations, or at least one solution of these equations that is non-trivial, is of this form. Okay, and so we're going to think about these solutions for quite a bit. And so let's look at them. The solution for the electric field is telling me that the electric field, which is a function of position and time, so you're measuring the electric field at some position and also at some time, right? I can just sit in that position and let just time evolve, right? So the solution of the electric field at this position and time is equal to E naught, where E naught is some constant and is an amplitude. It's telling me how strong the electric field is at that point, right? If E naught is 0, then the electric field is just absolutely 0. If E naught is some higher number, bigger than 0, of course, then it's going to tell me the amplitude of this. It's going to tell me essentially the height of the wave, okay? And then what you see on the multiplying E naught is a cosine with a seemingly complicated argument, but it's not that complicated, okay? If we look at it in some detail. So you see that x appears here and time appears here. So position and time. And also for simplicity, I should have emphasized, but what I'm thinking about is just a one-dimensional space, okay? I want to make my life easier. I don't want to think about three electric fields or magnetic fields evolving in 3 dimensions. I'm just thinking about them evolving in 1 dimension, okay? And that's what x is. But time is important here. I need to let time evolve to be able to see the evolution of the electric fields. And so x is the position, t is the time. I have factors of 2 pi, easy enough. And then here I have this lambda, which is the wavelength of the wave. And t and f is the frequency, okay? If you look at the magnetic field, it has exactly the same solution, okay? And except here you have a prefactor b naught, and that's it. Essentially, everything else is the same. These expressions are slightly more complicated in 3 dimensions, and there's some details that I'm sweeping under the rug, but essentially, this is good enough for 1 + 1 dimensions. Okay, so let me talk about the different idea of, or the definition of each one of these objects. So first, hopefully the amplitude is clear, but I have some pictures in just a second that I think will clarify this in some more detail. So I'm going to put that aside for now. The frequency, that might sound familiar, and you perhaps have a good intuition, and hopefully it's right, but basically the frequency is just equal to the inverse of the period. So 1 over the period, and it's defined over here. And the period is just the time that it takes for the wave to complete a full cycle. So basically you can imagine if a wave is just a series of peaks, right? It's the time that it takes from one peak to pass you, and then the time that it takes, or it's the time, once a time, so if you have a peak that passes you at some instant, the period would be the time that it takes for the next peak to pass you, okay? So that's the period. And the wavelength is the separation, is the length between the 2 peaks, okay? And as I said, in 3 dimensions, electric and magnetic fields, the expressions are slightly more complicated, and there's the amplitudes have directionality associated with them, and these are correlated. But for the most part, this is essentially it for even for 3 dimensions. And here's a little animation of how the waves look like, at least in some for one simple example, where you have the wave moving towards the right, and you can see essentially the planes that define the front of the wave, and you can think of them as being at the peak. These planes are perpendicular to the peaks of the wave, and let's look at it one more time. So this is telling you where the peak lies, and then the separation between the planes is exactly the wavelength, okay? So it's the distance, the wavelength is just a distance between these two planes. And you can see that the wave is moving forward as it goes through a peak, and then another peak, and then another peak, okay? Okay, so this is exactly, in fact, the solutions to Maxwell's equations in this region where you have no charges, and these solutions represent these electromagnetic waves, which are just the evolution of these electric and magnetic fields that are coupled together, traveling together. And I should have said that in this three-dimensional picture, the red is the electric field and the blue is the magnetic field. Okay, and so they're traveling together. Okay, so the sinusoidal solutions can be described in terms of the wavelength and the frequency. But these are actually not independent of each other. They're fixed by this constraint. The speed at which waves travel has to be equal to the frequency times the wavelength, right? And this makes sense, right? The wavelength is a distance between two peaks, and the frequency is the amount of time that it takes that peak to get there, right? For the second peak to get there. And so the speed at which the wave is traveling is the speed of, let's say, just one peak, right? So that would be equal to this. So it would be the wavelength divided by the total time, the total period. That's equal to the frequency. And so they're constrained by this. And so all electromagnetic waves travel at the same speed. And the variation between them is either what the frequency is, or equivalently, what the wavelength is. And so here's a little depiction of the difference. So on top, you see the wavelengths of different electromagnetic waves. And then correspondingly on the bottom, you see the frequency. And this frequency has to be equal to 1 over to the speed of light divided by the wavelength, okay? So they're constrained that way. And so you can see quite a few waves that are familiar to you, right? Radio waves, microwaves, infrared. Then you see the visible light, right? This is the light that we can see. And you can see it exists in this region between 400 nanometers in wavelength to 700 nanometers, right? That's the frequencies of which our rods in our eyes are sensitive to. And then after that, at higher and higher frequencies, you have ultraviolet, X-rays, gamma rays, and so forth. So another way to think about this, to give you some sense of scale of how big these waves can get, it's useful to write down the wavelength up here. You can ignore the wave numbers and electrovolts, and you can just go to the frequency. Okay, that's good enough. And so here on top, you can see some size of objects that you perhaps are familiar with for some reference. So you have a football field, which is roughly, I think it's bigger than a soccer field. Person's height, baseball, paper clips, the thickness of paper, cells, bacteria, viruses, water molecules, atoms, subatomic particles lie over here. And so for some reference, you can see what is the size of the different electromagnetic waves that we see. So AM, FM radios lie over here. Cell phones go roughly at this frequency, radars. What do we see here? Bioimaging, and then a bunch of other objects, okay? And maybe on the right, you can see that as we go to smaller and smaller distances, we're going to higher and higher frequencies, right? So if the wavelength is smaller, then the higher frequency has to be. And you can see that things that have a smaller wavelength are useful for resolving things that are smaller, right? That makes sense, right? the smaller the wavelength is, the more we can be able to it can probe objects that are smaller, right? And so higher frequency objects are exactly what we need to be able to see, for example, or high frequency electromagnetic waves are exactly what we need to use, for example, to see subatomic structures. And that's what we use at Jefferson Lab. We use a high frequency, essentially high frequency light. Or electromagnetic waves. While things that are bigger, or wavelengths that are bigger, they're less sensitive to objects, and so they'll be able to travel longer and longer distances without being altered. And that's exactly why we use radio waves, which have large wavelengths, to be able to communicate over far distances, because they're gonna not be distorted by objects like birds, right, or trees, right? They're gonna be much bigger than that. Okay, so to give you a little bit of time to digest these ideas, I'm sure you've heard some of this before. I figured I would have a conceptual question, which is a little gimmicky since you can't answer. So I'm gonna assume you get it right, and you're free to just type the answers, and the TAs can confirm that you get it right. But here are the 3 questions. So first, ultraviolet waves have a shorter wavelength than infrared. Which one of them has a higher frequency? Okay, good. Radio waves have a longer wavelength than microwave. Which one of them has a higher speed? And you see your options right here, right? Light having frequency, wavelength, and speed is traveling through an empty space. If the frequency of the light were doubled, then its new wavelength would be all right. Give you a second. You can try to type your answers. There's going to be a delay. So, but, all right, good job. You get it right. I don't know. I assume, I hope. So, ultraviolet wavelength waves have a shorter wavelength than infrared. Which one of them has a higher frequency? Ultraviolet, right? The shorter the wavelength, the bigger the frequency. Here we're talking about the different wavelengths between 2 different waves, right? And we're asking about the speed, but they all travel the speed of light, right? The product of the frequency and the wavelength has to be equal to the speed of light for electromagnetic waves. And then finally, if I were to double the wavelength, if I were to double the frequency of a wave, then the new wavelength has to be half, so that the product of the 2 stays fixed. Okay, does that make sense? Hopefully it does. Okay, so having introduced these concepts, what we're going to do now is just have a little bit of fun with that. Okay, so first we're gonna, instead of deriving these solutions and explaining you where they come from, the idea is that we have a numerical tool at our disposal. And so you should feel, hopefully, a lot more comfortable to, even if you see an equation and you don't know where that equation is, but you see some solution to it, either hopefully now you're able to more comfortably derive some equations that perhaps you weren't able to before, but hopefully you're also much more comfortable testing solutions to equations. And so here, what we're going to use is tools that you've already learned to test that indeed the solutions satisfy this wave equation. So instead of showing you, just test it, right? You shouldn't trust me, right? I mean, hopefully you trust me a little bit, but science is about, the core of science is a little bit of skepticism, right? We need to test each other's idea and push each other to be able to push each other forward. So what's one way for you to test this using what we have already learned? Well, first, you saw these fancy derivatives, right? They're calligraphic rather than these like simple D's. So this is a partial derivative. Don't worry about that. That doesn't matter. Just it does exactly the same thing. All it's doing is that I'm taking a derivative with respect to x here. I'm fixing t. That's all it means. And here, when I'm taking a derivative with respect to t, I'm fixing x. That's all it means. Easy. But what we're going to do is replace the derivatives, right, with its definition, which is the difference between the function at plus a minus the function minus a divided by the distance between these 2 points, which is 2a. We're not going to take a to 0, right? Because we can't do that numerically. That doesn't make sense. It's not clear how to take this limit numerically. What we can do is evaluate it for a bunch of a's and test the convergence, right? And so what we're going to do is just grab this expression for the derivative and just rewrite this so that we just act this difference twice on the left-hand side with respect to x, on the right-hand side with respect to t. Okay? And so what we're going to do is test that these are indeed solutions, given that lambda and the frequency have to be constrained by this, right? But E naught, it's not constrained by this equation. And so what we're going to do is evaluate this derivative numerically separately, and then this derivative separately, and then show that they're both equal to each other, or equivalently that the difference between the two is 0. Okay, so in some principle, you can just go ahead and do this, right? You have all the tools at your disposal to do this. So I'd encourage you just to do this without seeing my code. So here's an example of where I test this in my code. So first, I felt lazy. And so instead of introducing the speed of light to be 3 times 10 to the 8, I decided to set it equal to 1. Why not, right? This equation should hold for any speed of light, right? Regardless if it's 1 or whatever other value it may be, right? And so I defined my E field equation. I set the speed of light equal to 1. I didn't put as many comments because it gets a little cluttery. And so this is just my expression for the electric field. And I'll show you some plots, and so you can test that what I'm doing makes sense, okay? And then I define dE, which is the first derivative on the electric field. And notice I did something clever. I'm going to take the derivative with respect to x and also with respect to t, right? And I don't want to write different functions for each one of them, right? They're the same function, right? I'm just grabbing the differences between 2 points and dividing by 2a. And so what I did is that I introduced a string, which is variable. This is var, which is short for variable, which is the variable with respect to which I'm taking the derivative, okay? And so if var is equal to t, I'm taking the numerator is going to be the difference of the electric field displaced in time, right? While if the variable is equal to x, then the numerator is going to be the difference of the electric field displaced in a. And then the denominator is exactly the same for the two. So that part is universal. And so then I just divide this by the same denominator. Okay, that's the first derivative, right? What do I have to then do to calculate the second derivative? Well, I can just calculate the derivative of the derivative, right? And I could have done this more cleverly, but it doesn't really matter. You can just do things that are less clever but are more clear. And so that's exactly what I did. I decided to define a second function, which is dE2, which is a second derivative of the derivative. And it looks exactly the same as dE, but instead of taking the difference of the electric fields, I'm taking the difference of the derivative of the electric field. Structurally is the same, okay? And then the test of the electromagnetic waves, all I want to do is just grab the derivative with respect to t and t twice, right? You see this one depends on two variables, var1, var2. And here I'm making, so it gets a little tricky, and so you have to look at it carefully. But the second derivative with respect to t, so it's taking the derivative with t twice, and the second derivative with respect to x, the derivative with respect to x twice, okay? And then I just plot the difference. That's basically it, okay? All right, so hopefully that was clear, and hopefully you can write your own code to test these solutions. So I would encourage you to do that. So let's see what kinds of plots I've generated, and I would encourage you to try to generate similar ones. So I picked some value of the height. So what I did is that I varied different frequencies and different heights, and I made sure that my solution satisfied the wave equation. And notice I decided to fix x to 0 because it doesn't really matter. This solution should hold for any values of x. I set the speed of light to 1, and then I varied the other parameters. So first, here's the solution. If I set E naught equal to 1, so that's light, right? And then the frequency is equal to 1. And so first, notice the height is this value, it's this distance away from 0, and it's 1, consistent with this. So that makes sense, right? The wavelength is equal to the speed of light, which is 1, divided by the frequency, which is 1. And so the wavelength has to be equal to 1. And you see, that's the distance, as I mentioned, is the distance between heights, right? That's the length of the wave. And you see it goes from 0 all the way to 1. So that makes sense. Good. Then I just took the derivative with respect to x minus the derivative with respect to time, and this is what I got, 0. It was actually much, it's in the order of 10 to the negative 18 or something like that, so which is just numerical noise. I mean, it's or discrete effects associated with A, but here I kept the height the same, but then I varied the frequency, and notice I made the frequency bigger, which then makes the wavelength smaller, right? I kept the speed of light fixed, and so if I make the frequency bigger, that means that the wavelength has to go down, and you can see then, and it has to be 1 over 1.5, and that's indeed what you get. So this is now the new wavelength, which is smaller and less than 1. Good. Then I just repeated this for a different height, same first frequency, again, satisfies the solution. And then I varied now the height and the frequency, and I got this other solution. So very good. Hopefully you can try to reproduce this, convince yourself that these are indeed solutions to wave equations. You shouldn't trust me. You should be able to do this on your own. Okay. All right, so why don't we keep going? So now that we have defined waves, we can go ahead and observe the fact that most of the light that we see is not wave defined by a single frequency, right? In fact, it's defined by many different frequencies. And here is a canonical example of white light that is being dispersed into or refracted into all the visible light frequencies that we can see. And so you see the rainbow right there, right? And so that's telling you that this white light was actually a superposition of all these different frequencies. What does superposition mean? It just means just add them up. Just grab all the different waves with different wavelengths and just add them up all together. So it's quite simple conceptually. And in fact, adding these up numerically is even easier. It's just simply just summing up. And just to illustrate this, this is your second exercise. Just try to reproduce these plots. So on the top, I'm plotting a single wavelength for a particular value of n, right? And what this, here I'm fixing the intrinsic frequency, let's say, to be some number. And then what I'm just varying is a number, oh no, I think I meant to say, I think there's a typo, but I am varying n, I'm setting the frequency, intrinsic frequency to 1. I'll show you what I mean in a second. So on the bottom, what I'm doing is adding up all the waves that are appearing on the top, okay? So right now it's just a single wave. I scale this differently, right? You see the height here is 2, while here the height is 6, right? So it looks a little bit different, but it's in fact the same wave, right? It has a height of 1. I've set the height to 1, right? So I forgot about the coefficient in front. So the height is 1, and so it goes from 1 to -1 back to 1, okay? And this goes from 1 to -1 back to 1, okay? Good. So now what I'm going to do is add another wave that has double the frequency, and I'm going to add these up together. And you see that now these added together, now the pattern starts to get more interesting, right? It looks like at certain points, like here, it amplifies, right? But at other points, it decreases. So for example, here you see that they're destructively interfering with each other, right? And if you remember back in Dr. Aslan's talk, she showed these double slit experiments for water waves, and you saw that at some points the waves added together, they amplified, and other points they canceled with each other, right? So you had nodes, you had points where previously you had some amplitude and they were replaced with zeros, okay? And so this is the mathematical representation of that. This is what you're seeing. You're seeing different waves just being added together and create constructive interference or destructive interference at some other points. And we can keep doing this, right? Now I'm going to add 3 by just tripling the original frequency, and the pattern starts to get more interesting. I can multiply it times 4, 5, sorry, and this is what I get. So that's pretty easy. So you should be able to reproduce this plots with no new math, essentially. It's just grabbing the different waves and adding them together, and you should get patterns like this, right? And this is really what now more realistic depictions of waves, for example, sound waves or light waves, really look like, right? They're a juxtaposition, they're a superposition of different waves traveling with different frequencies, okay? So that's quite easy, right? And so we can then plot these as a function of time, and this is what, and from now on, although I'm originally interested in electromagnetic waves, which depends on, and any wave will depend on both position and time, I'm always envisioning from now on that I'm fixing position to be 0. So I'm at some point, and I'm just seeing the waves traveling to me, and I want to understand these waves, okay? So now imagine that you see this kind of wave, and I were to ask you, and let's say this is light, right? And I were to say, wait, what frequencies of light are present in this wave, right? Or imagine that I wanted to, just want to break them up into different components and be able to definitively say, one of them has, this has a frequency associated, a frequency of 1, 2, 3, 4, right? What would be the answer in 5 in this case? How do I do this? And the answer is that this can be broken up into this different constituents using Fourier transforms. And so that's what we're going to introduce towards the second half of the talk. But to see intuitively what Fourier transforms do, what we can do is just grab this wave, or what I'm going to do is just grab the different components of this wave. I know what the components are. They're defined like this. They're just cosine 2 pi times n times t, okay? And so what I'm going to do is multiply each one of them. In fact, I'm only going to plot 4 of them, not 5 of them, and multiply each one of them times cosine 2 pi, okay? So that's easy. So let's just look at it. This is what I get. So for n equals 1, which is, so I'm just plotting the cosine of 2 pi times t, times cosine of 2 pi n t. Okay. So first, let's look at the top panel. So n equals 1, and I'm plotting this as a function of time, just as before. I made a smaller sliver going from -1 to 1. And if I look at the top panel, you see that this is always positive, right? And why is that? That's because I'm taking the product of a number times itself. And as long as a number is real, the square of a number is always a positive number, right? And so this is just a positive number. And so it's always positive. While the other ones, if I look at them, they have positive values, right? But then they dip to negative values, and then positive again, and then negative again. And if I were to look at the negative values, it looks like I have just as much positive values as I have negative values. And here you see some positive values, here's some negative values. And so it seems like there's as much positive values as there's negative values. So if I were to be able to sum all the positive values and subtract all the negative values of this area, then that would lead to something that is not quite 0, but maybe very close to 0. While this one is going to be a much bigger number, right? And so it's suggesting that if I were to sum, if I had a way for me to sum the area, then the total area of this is going to be some positive big number, and this is going to be some small number. And so what we're going to do is take a little detour to think about how to sum up these areas continuously. And so you can guess where we're going. We're going to calculus. So maybe this is a good point to take a little break, see if there's any questions. Maybe what I'll do is take a break. I'm going to take a 5-minute break just to give my voice a rest, and I'll let the TAs see if there's any questions, and we can cover them when I get back. All right, and we're back. Any questions, comments, or anything to cover before we continue?
Yes, Raúl. There are 2 questions, and we go in this order. The first one is from Kiara Rivera from Coamo, Puerto Rico, asking the following. When we set C equal 1, is 1 the amplitude of the wave? And I will try to answer that. And no. Basically, what we are setting is the speed of the wave. We are setting it to a fixed number, and it's 1. We agree that the wave moves with a constant velocity, and in C we are putting 1 for simplicity to make the code easier. Nothing special there. The second question is from Jeju Leo Chu from Chaji, Taiwan, and he's asking, can you clarify how to apply the regular differential equation solver to a partial differential equation? I'm confused which variable to differentiate.
Very good. Yeah, so the partial differential equation, in this case, you see there's a calligraphic dx, and what that means is I'm going to take a difference. I'm going to see how the electric field changes with respect to x while keeping t fixed. So t is not change here, okay? And so, in fact, my code makes this very, very explicit. So here, for example, this code is taking a difference, let's say, on t, right? So I'm evaluating t at plus a, and then I'm taking t to be t plus a, and then t minus a. But notice, x does not change. And so that is the definition of a partial derivative. Wait, sorry. Was the question asking about partial derivatives or partial differential equations?
Partial differential equations.
Sorry. Let's go back. So a partial differential equation is just when you're taking is an equation where you're taking derivatives with respect to multiple variables. So up to now, we've always assumed that there's only a single variable. For example, in the SIR model, the independent variable is time, right? And so everything evolves with just time. but things get more complicated if your functions don't just vary with respect to time, but also position, right? And so because of that, these are different differential equations where we're taking derivatives with different variables while keeping the functions. So here we're taking a derivative with respect to x while fixing t, and here we're taking a derivative with respect to t while fixing x, right? And so these functions are, in this case, they depend on two variables. So you can imagine that they'll have some value for a different range of parameters which live in a plane of x and t, right? And so it just becomes slightly more complicated, that's all. Okay, any other questions?
Can you hear me?
Yeah.
There is another question from Jeju Liu Cho from Taiwan. He's asking if you can elaborate what n means in the last slide. It is taking the n amount of cosine wave with f starting from 1 all the way to n?
Yeah, this shouldn't have, yeah, this was a type, I'll fix this. But basically it should be, what I'm varying here is the frequency on top, and then I'm summing over all the waves, okay? And so really what I meant to say is that what I'm varying here is n, not f, and I'm fixing f to be 1. Okay, so if I fix f to be 1, and then I set n to equals 1, that's equal to this one. Then if I set n equals to 2, that's this one. So what's wrong is these labels right here. And I should have put that f is equal to 1. And then this is right. Okay, hopefully that clarifies that. So sorry, it was a typo. I'll fix that. Okay, I think we could probably move on. Is that okay? Good.
Yeah, I think so.
Okay, so our task is to try to figure out a way for us to evaluate the area below these curves, and with the hope that they can tell us about which are the frequencies that are underlying. And we can see here that by picking the frequency of 1 and multiplying that times the frequency of 1, I get something that looks like the area is positive, while the other ones, if I do that if I multiply this wave, which one frequency and multiply times another wave, then there's interference between them, right? And so it looks like the area is not quite positive, or at least it doesn't. It looks like if it's positive, it's going to be much smaller than this one. So that's the idea. So to do this, well, we got to go back to our friend calculus, which I've introduced a couple of times now. And the basic ideas of introductory calculus is that there's two different concepts, and they're closely tied to each other. The first is differential calculus. So this is where we're interested in rates of change of functions, and we've been thinking about this quite a bit. The second one, which is what we're going to think about, is integral calculus. And here the goal is to evaluate, we're interested in evaluating continuous sums of functions, or equivalently to evaluate the area underneath the curve or the area between two different functions, or the area covering two different functions. And this, as I said, we covered in the 6th lecture series, so go back and check that out if you're interested in a refresher, or you haven't thought about, or you skipped that class. And so what we learn about today is the second one. It's trying to address this question of how to evaluate the area underneath a curve or evaluate continuous functions. And so let's go ahead and do that. And so the problem that we have at our hands is this. So one of the main goals, or one of the first things you learn when you start thinking about integrals, is to evaluate the area under a curve. And this, what it really means is that if I want to evaluate the area between two lines. In this case, I'm thinking about a line, the first line, which is the function that I'm interested in. And the second line is a horizontal axis. And so here I've multiplied two different cosine functions, and I plotted them as a function of x. And so here what I'm doing is I'm emphasizing exactly what's the area that I'm interested in. So what I'm interested in is the area that is between the function that I'm plotting, which is this line, and the horizontal axis, right? And you see that some area is above the real axis, while other areas are below the real axis. And so the question is, what is the sum of this total area? Keeping track of the fact that some of it will be positive and some of it will be negative, right? And this is actually, mathematically, it's a little challenging to evaluate integrals, but numerically, it's actually quite easy. And so hopefully this convinces you of how easy it can be. So what we're going to do is think about some generic function. So here I've zoomed into some function that I'm calling f of t, which depends on this independent variable t, right? And here's the function that I'm plotting. And I want to plot the area underneath it. And so that means I want to plot all the area that lies between this line, this black line, and the horizontal axis. And so what we're going to do is not evaluate this directly, but instead we're going to approximate this with a way, in a way that it would become increasingly systematic, okay? And so what we can do is replace this area with a much simpler area, which is the sum. I'm just going to replace this continuous function with just a bunch of rectangles, okay? And so what is the definition of these rectangles? The rectangles are defined first by a width, which is this delta t. I'm going to introduce a value of delta t, which is the separation between nearby points. And this is a parameter that I'm going to be able to vary, okay? And this is the same delta t that we introduced to be able to take numerical derivatives, okay? So delta t is that parameter. So that defines the width of each one of these boxes. And for simplicity, I'm going to assume that each one of these boxes has the same width. They're all delta t, okay? So that covers the width. Now the height. The height is defined by f evaluated at some value of t. So here I picked out some random value, some particular value that I'm going to call t sub n, okay? And so the function at that point takes a value of f evaluated at t sub n. And so what I'm doing is that I'm defining the height of this rectangle by the value of this function. So that the value of the function is this value, and the height is just the difference between this and 0. Makes sense, right? So now what I've done is separated, I've defined, and I can do this for every value, right? Every value of t, I just picked one value and I'm generically calling it Tn. And the beauty of this is that I know exactly what the area is for this rectangle. It's just equal to the height, which is f t of n, multiplied times the width, which is delta t. And so all I have to do is just evaluate the area for each one of these boxes, for each one of these rectangles, and just add them together. And that's going to be my approximate for the area underneath this curve. That's the basic idea of calculus, okay, or integral calculus. So how do we do this? How do we notationally represent this? Well, I'm interested in the area, so I'm calling that A sub n, and n is the number of boxes, okay? So each one of these objects, it runs from 1, right? I have one box all the way to capital N, and so n here is just the number of boxes, and I'm gonna add up the area for each one of these boxes. And the area is equal to the width, as I just said, which is the same width for all of the boxes, right? Multiply times the height, and the height is just the value of the function evaluated at the center in the independent variable of t, okay? In fact, here I could pick any value that is inside of this box for the function. So that, you have a little bit of freedom. So ultimately, what we want is not this approximate for the area, but we want to get the actual area underneath the curve. Well, how do I improve upon this? I improve by taking the width of each one of these boxes to 0, right? And so as I take the width of each one of these to 0, well, I'm going to need more and more boxes to be able to fill in the whole area, right? And so I'm taking the width of each one of the boxes to 0, but I'm taking the number of boxes out to infinity. This is, maybe conceptually challenging, but that's essentially what we want. We want to take the number of terms to infinity, and we're summing over infinite number of terms, each one of an infinitesimal size, such that their sum is a finite number. Okay. And so we give this limit a special symbol. And I should emphasize here, this sigma, this is a capital Greek letter sigma, which is telling you that you're taking a sum over points, and they're discrete points, and they're labeled by this index n, right? And it goes from 1 all the way to capital N. Notice the value of the function is the argument of the function depends on this choice in n, right? But the delta, this width does not. Okay, I made this to be the same. And the Greek letter sigma is this is capital Greek letter sigma is equivalent to our capital S, and it's chosen because it represents sum, right? So we're just doing a sum. So S, sum sigma. The limit in which delta t goes to 0, or equivalently as n goes to infinity, right? This is still a sum, right? All we're doing is just making a sum, but it's just a fancy sum. And so what we do, instead of using the sigma symbol, we give it a calligraphic S. So it's a fancy capital calligraphic S, reminding you that you're still, at the end of the day, doing a fancy sum. And here, the way that this is symbolized is that, again, the argument is the function that you're trying to evaluate. We've replaced this delta t with dt, which is the infinitesimal form of delta t. This is the same dt that appears when you're taking a derivative, right? So derivatives and integrals are closely related to each other, right? And so dt is the same symbol, and that appears here. And then the two things that appear here are the initial value of t and then the final value of t. So it's telling me where I'm integrating. I'm doing this sum of terms, and it's going from here all the way to some final value, tf. And it is this limit, this thing, that is called the integral of f in the range of t going from ti all the way to tf. So this is an integral, this limit. In practice, right, we're not able to take this infinitesimal limits, right? When we're doing things numerically, we can't actually take delta t all the way to 0. And so, in fact, what we can do numerically is just evaluate this for increasingly small values of delta t and test the convergence of these results and show that they're indeed independent of the choice in delta t that we picked. And this is exactly the same concept that we use for taking numerical derivatives. So hopefully this is now much more clear. Okay, so, and I should have emphasized, this is called a Riemann sum. The limit as delta t goes to 0, the sum, the limit of the Riemann sum is equal to the integral. Okay, so now you're familiar with all the jargony stuff. Why don't we go ahead and put this into practice into 2 exercises, 2 of which we know what the answer has to be, and so this will test your intuition and test that you understand how to evaluate integrals. And trust me, if you can do this, you can pretty much do any numerical integral there's some challenging integrals out there. I think Connor, I see Connor smirking because he's working on a highly complicated numerical integral for one of our projects. So there's some numerical integrals that are really challenging to evaluate. But for the most part, a lot of numerical integrals you can evaluate with techniques like this or slightly generalizations of this. Okay, so the first exercise is the following. Let me fix my graph, which is we're going to plot the function that I've labeled there, which is f of t is equal to 1 plus t. And we're going to evaluate the area underneath the curve from 0 all the way to 1. Why are we going to do this? Well, it's not so trivial, and it's sufficient to test our ideas, but also we know what the answer is. And the answer is quite easy to find. We know that the area underneath this curve, so the integral of this function, which equals the area underneath the curve, has to be equal to 1 plus 1/2, which is also known as 3/3. Why is that? Well, I've suggestively put some dash lines. I've put the limits, right? So this is 0 right here. This is 1, right? And so what I'm interested in is the area in under this curve, right? And we don't have to do anything fancy to just know that the area has to be this. And the reason why is because I can grab this function, I can grab this area and write it in terms of two different areas. One is of a square with a length of 1, right? So this goes from 0 all the way to 1. And here I'm ranging the height from 0 all the way to 1. And so this area has to be the area of a curve of length 1, which I know is equal to 1. This is the area of a right triangle of length 1 and height 1, which has to have the area of half of a square of length 1. So that has to be 1 divided by 2. And so the sum of 1 plus 1/2 is equal to 3/2. Easy, right? Not so hard. But obviously, we're not interested in just evaluating this analytically, right? This is a course where we're evaluating things numerically, and we introduce the concepts on how to evaluate this numerically. So how do we do this? Well, we use the idea that we introduced in the previous slides. We just grab this area, and we break it up into tiny little boxes of length delta t, the height defined by the value of f of t at that particular value of t, right? And we just sum the area for each one of these boxes. Doing this is relatively straightforward, or conceptually straightforward. Writing the code takes a little bit of time, but that's what you're here for, right? You're here to write your own independent code and be able to evaluate these types of integrals. And so here is my code where I'm evaluating just using this algorithm for the area as a function of delta t. And here's my expected value. I've used the fact that 3/2 is equal to 1.5, right? And so what I obtain are values that are oscillating for a particular choice of delta t. They're oscillating around 1.5. And then for sufficiently small values of delta t, they start to converge to 1.5. Okay? So the first task involving integrals is for you to reproduce this figure. Okay? So hopefully it's clear. And if it's not, why don't you write your questions? What are the things that we need to clarify? And we'll have a second to have some to answer your questions. But before we answer your questions, let's now apply this to evaluate another integral or another area in this case, and recalculate pi. Remember, way back when, in the third week of this course, you evaluated pi statistically, right? Here, we're going to do a slightly better determination of pi using integrals. And so this time, what we're going to do is just grab the same concept, but the previous concept of evaluating areas inside of curves, but for a circle. And I'm going to define a circle to have the radius of 1. We know the area of a circle has to be pi r squared, right? But if I set r to be equal to 1, the area has to be pi. And so how do we do this? Well, just grabbing the same crude idea, right? I'm going to just replace this with boxes. So I'm going to create a box that goes from -1 to 1 along the x-axis and from -1 to 1 along the y-axis. And then each one of these boxes I'm going to break up into smaller boxes. And each one of them is going to have a length of delta x. If the center of the box lies inside of the circle, I'm going to label it as red, just like this, right? And I know the area of each box is going to have to be delta x squared. And so at the end of the day, the whole area of the circle is just going to be the sum of all the areas of each one of the red squares. And this algorithm, of course, gets increasingly precise and accurate as I take delta x to 0. And so having done that, well, just determine pi as a function of delta x and show that indeed you're converging to the right answer. And this is my code. So I just sample all values of x going from -1 to 1, all the values of y going from -1 to 1. I calculated the distance away from the origin. I made sure that the distance is less than or equal to 1. If that's the case, then I evaluated the box associated with that center value of the choice of my x and y parameters. And then I added that to the area, and I just loop over all possible boxes, adding them together. And this is what I get. I get some values that are underestimating the value of pi, some that are overestimating, and you see that it starts to converge for sufficiently small values of delta x. And so this is a goal, right? Is for you to be able to reproduce this just using these techniques. Okay, so hopefully those exercises are clear. If not, now is a good time to answer your questions if you have any. So perhaps the TAs can let us know if there's any questions to be answered.
Raúl?
Yes, Juan?
There is a question from Yayu from Taiwan. It says, just curious, how do you know that the area will not go to infinity if you are taking infinitely many areas? Or does it depend on the function?
Certainly it depends on the function. But if the function is finite in that area, you're taking an infinite number of terms, but the contribution of each one of those terms is going to 0. And the way that these limits, right, you're taking, in one way, you're taking one quantity to infinity, and the other one, you're taking that quantity to 0. And the question is whether that limit is well-defined or if that limit is a finite number. And for the examples that we're considering, they're definitely finite. They're well-defined and finite. And so some integrals do lead to infinities, and those are trickier. These techniques don't work so well for them, but for the examples that we're considering, these are perfectly fine. And so you can test this, right? For the examples, this is the idea, right? Is to just get some intuition for what these limits are doing by just coding them up numerically for simple examples that you can convince yourself you know the answer, like this one, right? And you can test, I'm taking delta t to 0, and you can see that delta t is indeed going to 0, which means that for me to have evaluated this area accurately, which it seems to be because it's approaching the right number, I have to simultaneously take the number of terms out to infinity. I never in practice take that to infinity or the width to 0, but I approach that limit relatively quickly. Any other questions, or should we move on?
Nope.
Okay. Sounds good. Okay. So I think we're pretty close to the punchline. So having now introduced integrals, right, which are evaluating exactly what we talked about, right, the area underneath the curve. Now we can go back to this question of waves, right? How does this come back? How does this tie up to what we were thinking about in terms of waves? And so the exercise that we were after, right, is imagine that I have some signal, and I know the signal is a superposition of different waves. And I want to be able to determine which frequencies are present and what their contributions are for each one, from each one of those frequencies to this total signal. And what I alluded to is that Fourier transforms give us a way to do this. Fourier transforms, and I put the links here, so you can see the link on the PDF to a little description of Fourier transforms. And what they do is a way for us to relate this time-dependent functions to frequency-dependent functions, or in particular to relate into the underlying functions that appear. So they allow you to map from time to frequency and vice versa, from frequency to time. And so because of that, they play an essential role in modern physics. In fact, Fourier Transform are a lot of the bread. I mean, they're remarkable. I mean, we use them all the time in our research, so they're ubiquitous. And there's this really nice video that I don't have the time for us to cover, but I would highly encourage you to take a look at it. It gives you a nice pedagogical intuition as to Fourier Transform and what they do, the job that they do, or they do the claims that we're making here. And so, for the case of interest, imagine that I have some function, which is my signal, and it depends on time, and it's been determined in some time range of ti going to tf, okay? Then we can just go ahead and define what the Fourier transform is. The Fourier transform of this, which I'm going to denote as f hat, evaluated at k, where k is the frequency of interest, is defined as this. It's just equal to the sum of the function multiplied times this tiny little step in t times this exponential. But it's not really this. It's this in the limit that I take delta t to 0, okay? And we know in that limit, this thing just becomes an integral, right? And so the Fourier transform is the integral from the initial time to the final time of this exponential multiplied times the function that I'm interested in. Here, I is actually the square root of -1. So it's an imaginary number. That means that this exponential, in general, is going to be a complex number. And so if you're not familiar with complex numbers, I'm going to give you a mini introduction to them. And the first key equation that we can use is called Euler's formula, which allows me to rewrite this exponential in terms of functions that are more familiar to us. So in particular, we can write this in terms of cosine, a factor of I, and sine. And this is known as Euler's formula. And so this is a remarkably important relation in calculus, and we make use of it nonstop in physics. And so if we're interested in a function where our signal, f of t, is purely real, then this means that this Fourier transform has to be complex in general. And the real part of it, using this, just rewriting this expression above, and perhaps I should maybe use my iPad to clarify some of these identities. So give me a second. Meanwhile, I can see if the TAs have any questions that are arising or comments that are worth. Nothing? Are we good?
You're good to go.
All right. Well, you're going to have to give me a second. Okay. Okay. So let's just compare the expression we have just to make sure that we understand the algebra that we're doing. It's not that complicated, but we don't want to lose each other. So on the top, we have that f of k hat. The hat is just telling me that this is a different function, and so we're just giving it, we don't want to call it f. We want to denote that it's just a different function. It's closely related to f of t by this integral, but we want to make sure that it's treated separately. And so this is equal to the integral going from ti to tf of e to the minus I, how do we call it, 2 pi k of t, and then we have f of t dt. And the point is that I can write the exponential using Euler's formula as cosine 2 pi k kt minus I sine 2 pi kt. And so by just simply inserting this identity in here, we're able to write f of k as the sum of two terms. Cosine 2 pi kt minus I sine 2 pi kt. All multiplying f of t dt, right? And so you see I can separate these and just make this a little clearer. And then I have minus I over here for the second term. The range of the integrals is the same. And so you see that for a real f of t, I've written this in terms of two terms. One, which is the first one, which is just purely real. It's just a number, right? You give me some f of t, I multiply it times cosine, integrate it, just purely real in that time. While the other one is purely imaginary, because it has this pesky value of I. And I is equal to negative, is equal to the square root of -1, and it's an imaginary number. And so I can write this as the real part of f hat of k plus I times the imaginary part of f hat of k. And notice the imaginary part comes with a factor of -1, and so it's been absorbed into the definition. And so that hopefully explains what these things are. So the real part of f is equal to cosine times f of t, integrated, while the imaginary part is equal to negative, the integral of the function multiplied times sine in that range. Okay, so hopefully that makes some sense. And the beauty of this, though, is that for the functions that we're interested in, the imaginary part absolutely cancels. So we're considering functions that are going to be symmetric about t equals 0. We're going to evaluate them in a range where we take the same positive maximum value as the negative minimum value, okay? The magnitudes of the minimum and maximum are the same. And so that means that the integral of something that is symmetric multiplied times something that is antisymmetric in that range is going to be 0. And perhaps we can just illustrate this a little more clearly. So imagine we're thinking about functions that look like cosines, right? So let me just plot cosine. So cosine is a symmetric function. Let's call it this t is a independent variable, right? And so it's going to be symmetric about this range. And part of my drawing, there we go, a little better. And it's going to go all the way back up, okay? So this is cosine, but what I'm interested in is not the product of just the integral of this alone. It's going to be the integral of this with sine, and sine is antisymmetric. And so forth, right? And so what you see is that what I'm plotting, what I'm interested in is the product of these two. And because I'm going to determine this in a range where sine goes from being positive to negative, the product of these are going to exactly cancel in this region. And if you don't believe me, that's okay. You're going to test this numerically. You're going to test that both the real part is non-zero and it behaves as we expect, while the imaginary part is just 0. Okay, but fortunately, the imaginary parts do cancel for the cases that I'm considering. And it just comes from the simple fact that we're adding the same amount of positive area as we're evaluating the same amount of negative area, because one of the functions is symmetric while the other one is antisymmetric in the region that we're interested in. Okay, so hopefully that makes some sense. So now we can move on. And so having introduced complex numbers a little bit, I had to assume that you hadn't seen them. And I figured I would give you a mini introduction into them, just a one-slider. So here it is. And the reason why complex numbers are important is that they really appear in all physics, in all modern physics. And particle physics, for example, the functions that describe subatomic particles are complex in general. And this is actually made quite obvious and quite clear in the Schrodinger equation. So we saw the Schrodinger equation for a second on Tuesday, and this is what the Schrodinger equation looks like. Is a partial differential equation of the wave function of particles, where you're taking derivatives with respect to time, but also position. So embedded in here is the derivative with respect to position. And what you're seeing is that the object that is taking derivatives on the right is real, while on the left you have an explicit factor of I here. And so this function, this equation is a complex equation. And so the solutions of these equations, of these differential equations, are in general complex. Okay? And so this is just one of the many examples where complex numbers and complex functions play a role in physics. And so they're really important. And so complex numbers, you can most readily understand them by introducing what is called the complex plane. And this is just a plane that is defined by two axes. One is where the real numbers lie. These are the numbers that we have some intuition for. And then on the top and the vertical axis are imaginary numbers. These are just numbers that are scaled by a factor of I. So you can imagine 1 times I being here, while negative 1 times I being down here, okay? While here you will have 1, here you have negative 1. And so we can just think about these complex numbers as just living in this complex plane, and then we can just think about transformations and manipulations of these in the complex plane. And so just as a simple two examples to give you a little bit of intuition of what they look like, I'm thinking I introduce e to the I pi over 4 and e to the minus I pi over 4. And using the Euler formula, we can write this as cosine pi over 4 plus I sine pi over 4. If you plug this into your calculator, you will see that this will be 1 over root 2. Each one of them will be 1 over root 2. One of them would be a purely positive and real number. The other one would be a purely positive and imaginary number. And so we can denote this by just taking a step of 1 over root 2 to the right, right? That's what this is telling me. Take a step towards the right of 1 over root 2. And maybe we can do this on the iPad. Let's put them together. So I'm plotting a number. Let me call it, let's call it z, okay? And is equal to 1 over root 2 plus I 1 over root 2, right? And so I can represent this in the complex plane by just first taking a step to the right that is of length 1 over root 2. That is because this guy is telling me to take a step along the real axis. And so I take a step over here. But then the other one is telling me to take a step of the same length upwards. This is going to be 1 over root 2. And so I end up on this number. And if you see, if I take the hypotenuse of this, right, I'm just taking the square. If I want to calculate the length of the hypotenuse, right, I just take the square of 1 over root 2 plus the square of 1 over root 2, right? And this is just equal to 1/2 plus 1/2, right? Which even I can get to be equal to 1, right? And so that's telling me that the length from the origin is equal to 1. And so I can define this point in the complex plane with 2 coordinates. The first one is going to be the real coordinate, and then the other one is going to be the imaginary coordinate. And so this is just different ways of representing complex numbers. The second example is, and that's exactly what is being shown over here, is just different representations of complex numbers. The second example is eta minus I pi over 4. Same thing as before, is that now if I use Euler's formula, I get a minus sign here. So you see that the imaginary part comes with the minus sign, right? And so that's telling me, if I replace this with, let's call this C prime. If I now, all I have to do is take a step to the right of this length, right? Of the same length as before. Let's make this green, right? Take the same step to the right. But now I'm going to take a step down because there's a minus sign, right? But it's of length 1 over root 2, right? Same length. And so I end up having this point, which has the same hypotenuse, right? And this is equal to this number in coordinates. I can write as the real part is just going to be 1 over root 2, while the imaginary part is going to be minus I over root 2. So it's pretty straightforward. And it turns out that for any number where you put that number inside of an exponential like this, as long as that number is real, it's going to lead to a point in the complex plane. In the unit circle. And it's just, you're just taking rotations along this unit circle by the phase introduced there. So that's quite nice, and this is used all over the place in physics, and so is remarkably important. Doing this numerically in Python is evaluating or manipulating complex numbers is actually pretty straightforward. The only subtlety is that in physics, we usually use the symbol I to represent the square root of -1. Python uses the symbol 1j. So you just grab the number 1, multiply it, or put it right next to j, the letter j, and that is the representation for the root of -1. This is more convention. This is more natural convention for engineering than physics, but it's okay. It's the same thing. And so you can use the same operations, the same arithmetic operations that you apply on real numbers. You can apply them on complex numbers. And so here I'm using IPython, which I like to use to manipulate numbers interactively. So I've defined x to be 1 plus 1j. Notice this lies outside of the unit circle because it has a length of root 2. So it's bigger than the unit circle. Here I've put another point that is also far off in the complex plane. It's going to be 2. So I take 2 steps on the real axis. And in fact, why don't we do this on the iPad? So the addition of complex numbers is pretty straightforward. So let me put x first. So x is, I take 1 step to the right for positive 1, and then 1 step upwards for 1 imaginary value. Okay. Then this is x, which is equal to 1, 1. Good. Now, y, well, I take 2 steps to the right. And then I'm saying that I'm going to probably run out of, oh no, I'm probably good. And then 1.5 steps up. So it is equal to y, which is equal to 2, comma 1.5. Good. And so I'm going to add these together, z, and call that z. Well, all I'm doing is just adding. Z is just going to be x plus y. And so what you do is that you add the real parts together, and you add the imaginary parts together. So what I should have is 3 plus 2.5. And sure enough, I added them together. I printed them out. I got 3 plus 2.5. And that makes sense, right? It just means I've taken two steps plus 3 steps, or 1 step plus 2 steps to the right. And so I land over here. This is 3. And then on top, I took 1.5 steps, followed by 1 more. And so I land over here. This is z, which is equal to 3, comma 2.5. So it's really straightforward in Python to manipulate complex numbers. And then if you want to return the real part of a complex number, you can just use this notation. You can just grab the number, then put dot, and then real. And that gives you back the real number, which is 3, the real part, which is 3. If I do z.imag, that's short for imaginary, it gives me back the imaginary part, which is the number right in front of the j, which is 2.5. So that's easy. The only tricky thing you have to be mindful of is that you can't make plots of complex numbers. Matplotlib doesn't know how to interpret it. So what you have to then do is specify which component of the complex number do you want to plot. You can plot the real part. You can plot the imaginary part. You can plot the magnitude, which is nothing more than the hypotenuse in the complex plane, right? Or you can plot the phase. I then define the phase. So, I mean, I hinted at it, right? So you can imagine this number right here. The magnitude of it is just the hypotenuse. The magnitude of x is just the hypotenuse. So it's just the length, right? And then the phase is the angle between the real axis and this line. And so in this case, the phase is going to be 45 degrees, also known as in radians as pi over 4. So you can plot any of those things as you wish. Sometimes the real part, imaginary part, absolute value, or the phases would be, one of those would be more relevant at some point. Okay, so then with NumPy you can use, not only can you multiply numbers, but you can also evaluate functions of complex numbers. So here I'm evaluating the exponential of a complex number, right? And I'm getting, something that is complex itself. So you can do this straightforwardly with NumPy. There's a little bit of limitations with NumPy. For example, there's no easy way for you to get the phase of a complex number, which is this angle with respect to the real part, to the real axis. But you can do that with another library called CMath. C meaning complex. So it's a library that allows you to evaluate complex different. It has a lot of routines built in with complex functions in mind. Okay, so that's my summary of my little introduction to complex numbers, both just mathematically and also in Python. So it's quite powerful. Python is quite useful for dealing for complex numbers. So I would encourage you to play with that. Okay, so I think we're reaching our end. So what I'm going to do is just give you 2 more tasks because I can't give you enough tasks, apparently. So you're obviously going to be able to do this at your own pace, and we're going to have the Slack chat open so you can send us questions and confusions that you might have. But what I'll do is that I'll introduce these 2, see if there's any last comments, and then we'll wrap it up, okay? So here are the last 2 exercises. First one, well, evaluate the Fourier transform of a specific function and see what it looks like. So here is a function that I'm defining, and I'm just summing. It's going to be the sum of 4 cosines, so of 4 waves, right? So it's just the sum of cosine 2 pi n over t, and I'm varying n from 1 to 4. Okay, so I'm setting the frequency to 1, 2, 3, and 4, and then I'm adding them together. And imagine that you've determined this from a time of negative 10 all the way to 10 in steps of 0.01. So you have a fine resolution of this, okay? And so the task is, first, plot the function, make sure it looks like this. Make sure I haven't made a mistake. Second, evaluate the Fourier transform of this function, both the real and imaginary part. I told you that the imaginary part has to be 0, right? So that's what you're checking for. So here is the definition of the real part of the Fourier transform using finite size mesh, right? So we're discretizing our time, replacing the integral with the sum of tiny little boxes, and that's exactly what this expression is doing. Okay, so evaluate the integral, the numerical integral, which is just this, for the real part, and then for the imaginary part, remember the minus sign. Not that it matters in this case. And then plot this function for k going from 0 to 10. And what you should see is this, right? Here, I have the function that I've determined. So there's the original function that is my signal. And what you see is that the Fourier transform of it, the imaginary part is 0, as I promised. But the real part, you see, is some wiggles, and then it peaks dramatically at the points at some specific values. In particular, it peaks dramatically at 1, at 2, at 3, and at 4. Why is this? Because what we're doing is multiplying this function, which is a bunch of cosines, with a cosine with some specified frequencies. And what we intuitively expected, right, is that the product of this cosine with some sum of waves is going to be peaked. It's going to be a larger value at the frequencies corresponding to the constituent frequencies of that original wave. And that's what we're seeing, right? We're seeing that this function, this Fourier transform, although it has some non-zero values and it oscillates, it sharply is peaked at the values of the frequencies that we built into this function. And so this is the worth of Fourier transforms. It tells us the information of the underlying frequencies of the functions that we're analyzing. So this tells us that this function, this signal, came from a superposition of a frequency of 4 waves, one with frequency 1, 2, 3, and 4. Okay, so we knew what the answer was here, and this is giving you hopefully a better understanding why Fourier transforms are useful, and you can see it with your own eyes. And so now with this, now I'll give you a last challenge. So, what a shame. I gotta have a typo on my last slide. Give me a second. Let me fix it. Okay. Okay. Last challenge. I'm going to give you some fake data. And the goal is for you to determine the underlying frequencies of this data. And I've generated it with some random frequencies. Okay? And you don't know what they are. And so here's a signal. It looks like noise, right? But it really is not. It's a sum over a finite number of frequencies. And so what you have to use is plot the data first, not plot the date, just plot the data. And then use Fourier transforms as we presented in the previous slide, and the same code that you've already introduced, right? You don't have to create new code. And use that to determine which frequencies were used to generate this data. That's it. Okay? So why don't we give you a second, see if you have any last minute questions, and we try to answer them. And then after that, we can say our goodbyes. Any questions and comments from the TAs that we're seeing? No? All right. Well, anything you guys want to say to the rest of the people out there, meaning the TAs? Any recommendations?
Raúl,
Yeah, Juan?
we had a comment from a while ago, but I didn't want to interrupt the sequence of the lecture, but this one is a good time probably for it. Come from Luis Ángel Vergara Ortiz from Hidalgo, Mexico. He says, nothing new to say, but I want to thank you all, not only the teachers, the TAs, but also the ones who are in this program for letting me know about ideas from different parts of my country and the whole world. This is ending because it kept my mind busy inside my house and found it interesting. Hope you will be this program. So he's happy for the program, and I guess that also all the TAs, and I talk on my behalf, I am very happy for the opportunity to help here and to contribute a bit. Has been a nice experience. I think that the topics were interesting and a lot of fun from my side.
That's really great. Thank you so much for reading that and for saying that, Juan. Yeah. Anybody? This is your last hurrah.
Yeah, can I add something real quick for going forward with this program? You mentioned that we're keeping the Slack chat up. Personally, I have a lot of trouble accessing the general feed for the Slack chat. So if you have questions, I would suggest, I don't know if the other TAs can second this, but if you send it to us directly as a direct message, I can answer it much more fluently. I can send it in the general feed as a response, but it's harder for me to get the information there.
Yeah, that's a good tip. Another thing you can do is if you tag people into the message, then people get the flag. So if you write, for example, at Raul if you put a message in the general feed and then you say at Raul, at Greg, et cetera, then it's going to ping us and we'll be able to be more aware of it. So that's a good tip, Greg. Okay, anything else? No? Okay, so I guess I'll say a few last words. So as you know, Python for Physics is part of the REYES program. And so this is a program that has been created in the very last minute with the help of volunteer faculty at ODU. They didn't have to do this, right? They did it out of the kindness of their heart. So I just say staff faculty at ODU, but also one Jefferson Lab scientist. And so these are people that have put a great deal of hours that are just volunteer hours to make this possible. So I think you should be grateful for this team. I mean, they're really amazing. And so the work that they've done is really extraordinary. So we should thank them deeply. And then second to last, I think we should be aware that this really wouldn't have been made possible with the distance learning team, which is behind the scenes, which has done all the work to be able to make this broadcasted live for you. And it was their idea on how to scale this up so that there was no barriers of who could enter, who could use this. And also they're the ones that are making all these videos available after the fact. And so really we have an excellent team here being led by Miguel Lamlanchan. So thanks to Miguel, Kevin, Scott, Dwayne, and everybody else behind the scenes. I mean, you guys have done a really amazing job. And you guys have been really helpful and patient with us. So extremely thankful for your hard work. And second to last, I guess, is really thanks for the rest of the team. So Ted Rogers, obviously, I mean, without him, I couldn't be able to do this, right? This is really a team effort. But really the TAs have done a tremendous amount of job, not just showing up here at each one of the sessions, but really contributing their own material to different extents. Later on, you know, Fatma gave us a really beautiful lecture, Introduction to Quantum Mechanics. And so these are, again, people that are just doing this out of the kindness of their heart, right? Like these are people that just care about science and making it available. And so they've done a really impressive job. So thanks to all of you. And so with that, I should say that this is the end. This is the last lecture for Python for Physics. This is not the last REYES activity. We have one more today, which is trivia night. And in fact, we might still be looking for trivia participants. So if you're interested in being a participant, send me an email right now to pythonforphysics@odu.edu if you want to participate. That being said, today is still not the end of REYES. So we most certainly have program activities for the next summer, so we'll come back then. But also, there's a very strong likelihood that we might do some special activities throughout the year. Not to the full extent as Python for Physics. There's a tremendous amount of work, and we can't really replicate this, you know, during the semester or throughout the year. But what we can do is host high-quality lectures for you. And so what I want to tell you is two different things. One, we're going to send you a survey asking you to fill out and give us feedback about REYES. Tell us honestly what you think, what we can do better, and so forth. Also, we're going to be asking to see if we can follow up with you going forward. I would strongly encourage you to say yes, because we have activities that I think are going to be of interest to you. And so after that, what we're going to do is send you further emails announcing these key activities. And so I would encourage you not to, you know, I know that everybody's going to be busy with your schools and different activities that may come up, but these are going to be special activities. They're going to happen perhaps once a month at most. And so these are not activities that you will miss out, and they won't take as long as this. So they're going to be key talks that will last maybe an hour long, but certainly do not miss this out. And as we said, all the material that you're seeing now is going to be maintained for you for posterity. You can keep using it. We're going to stay active in the Slack chat so that we can answer your questions and continue exploring the idea of perhaps getting you involved in some projects that are either simple or perhaps more challenging, and, you know, who knows, maybe set up ideas for future research projects. So stay engaged with us, and we wish you all the best in your different corners of the world. Stay safe.